wherever you want.
Where would be the most convenient? Amy, which word? In the center? Okay. Why would you pick the center?
I don't know, it's kind of like the standard, I guess.
Say it again.
That's, I guess, the most convenient place to put it.
Okay, just feels right.
Yeah.
Okay. Anyone else with another feel?
Yeah, I put it at the base of the ladder. That's
Why?
Yeah, part of me wants that too, because if it were to move, that's where it would move down.
Because it also makes it so that we get the answer to our question as our result. Because it's asking how far up the ladder. So if we start from the bottom. we'll
Oh,
find
okay.
the space
It removes one subtraction problem at the very end.
I suppose.
Okay. Anyone else?
Our lab group found it easier to put the axis of rotation kind of on the extreme end of the meter stick, just because it made all of the moment arms positive, instead of like some of them being positive and some of them being negative, depending on where the forces were applied.
That too.
That made it easier.
Okay.
Our little subtraction.
And that is an argument for that. Recognize also, when we did the equilibrium problem on Monday, I guess it was, and we could pick any place as the axis. We had the two forces acting up. We just had this single beam with a weight acting down. And we solved it with, I think, the left end as the axis to start with. And then we picked the middle, and then picked where one of the forces was actually being applied. Any of the things that were said, picking the middle, picking the lower left, I think those were the only two that were suggested. Either of those should get you the exact same answer. The question is, how much math do you want to do?
Oh, if we put it on one of the forces that are being applied, we can eliminate that one. Or it becomes equal to 0.
The torque does. Yes.
Right.
So, picking this would eliminate 2 torques. Picking here would eliminate 1 torque. Picking here becomes a lot trickier because now you're introducing an X into everything because we don't know exactly where this force is being applied. Picking this would eliminate 1 torque. But there are actually 2 other places, well, 3 other places that would also eliminate 2 torques. So the question is, where else can we pick a point where we are going to eliminate 2 torques?
Does it have to be on the ladder?
It does not. Therefore, thought you had a place in mind.
No, I didn't. I was just wondering if it had to be on the ladder.
Let's go to, that reproduced that beautifully over there. Torque is R cross F. And so the magnitude of the torque, R F sine of theta. So this is equal to 0 if R is 0, F is 0, or sine of theta is 0. And typically, if you pick the lower left, you're picking a place where 2 of the R's are 0. But where's a place where the sine of theta is 0?
When the angle is equal to, wait.
Zero or 180.
In other words, if the force is acted straight at the pivot point, so if I take this as my pivot point right here, this force is acting straight towards it. Technically, the moment arm is running like that, from my pivot point to where the force is applied. My force is acting back this direction. The angle between them, if I put them tail to tail, is 180 degrees. This exerts no torque about that point. Similarly, if I pick a point up here, where those two meet, I've eliminated those 2 torques. Because the angle between the moment arm and the force is 180 degrees, sine is 0, so there's no torque there. So That would eliminate 2 torques. That would, there, where those two meet, eliminates 2 torques. And in theory, yes, I could also pick the point right below where the person is standing, but again, that just complicates the math in that particular case. Now typically, if I were doing this, I'd pick the lower left corner, just as was suggested already. But I just want you to realize you can eliminate 2 torques other ways also. And we've done what we need for that. And all right, let's pick the lower left as first suggested. So we're gonna pick this as our axis of rotation. Because,
You said so.
who said it? I was thinking somebody first suggested it.
Oh, Ian
Yeah.
said it first. Ian said it.
All right.
This.
Amy was the first to suggest something, but I was going for the slightly easier math. I'm sorry if I'm depriving you of some math. Okay, I appreciate your forgiving. So now, I need to figure out my angles here. So ultimately, I'm doing my torque equation. Torque is equal to I alpha, and I haven't really gone into much detail what I is right there, other than moment of inertia. But conveniently, this is equal to 0, so I don't have to worry about it. So it's basically, I've got the torque from Y sub V plus the torque from the friction force plus the torque from the weight of the person plus the torque from the weight of the ladder plus the torque from Y horizontal. So that's it, 1, 2, 3, 4, 5.
Which ones cancel out?
That's 0 and that's 0, because in both cases, R equals 0.
That was friction. Yeah, friction and.
And the vertical, oh, I guess I eliminated that part. These two right here.
Okay.
So this is Y sub V, F sub S, this is W sub L, W sub P, or Y sub P, and this is Y sub H. Now we can just, there are a couple ways of determining positive or negative here. Probably the simplest one is the right-hand rule. This is my pivot point right here. Is the weight of the ladder trying to rotate it clockwise or counterclockwise?
Clockwise.
And so the thumb points in the,
Maybe
so from the weight of the ladder, that'll end up being negative. What about weight of the person? Positive or negative torque?
Negative.
they'll all be negative.
Y sub H.
We're gonna add up 3 negative numbers and get 0?
Our Y sub H torque is gonna be positive.
Positive,
Yeah.
because that's trying to make it, okay.
That's trying to rotate it around the other way, so that last one will be positive. So this is gonna be RF cosine theta, so now I have the directions down already, so I can now just look at this bit right here. I probably need more room than I just gave myself. So I have 0 minus R. What's the magnitude of the moment arm
For which one?
for the
Negative
person?
Yeah.
Times the magnitude of the force, which is 686, times the sine of the angle between them.
Wait,
Make-
between,
the moment arm and the force. So my moment arm is a vector going up like that at a 50-degree angle. My weight is acting down.
so 50 plus 90?
Times the sine of 140 degrees. Minus. Now the ladder. What is the magnitude of the moment arm?
Is it 10?
No, not 10.
Half of 10?
Yeah.
Oh, yeah. Wait, how do we know it's half?
I am assuming that the ladder is uniformly constructed and that the weight is, we can consider the center of mass of the ladder to be in the middle.
Okay. Oh, okay. At first I thought it had something to do with where the person was on it. And I'll
No.
save that.
Independent. Times the weight of the ladder, which is 98, times the sine of what is the angle between the ladder's moment arm and the weight of the ladder.
140 degrees.
Yeah.
It should be the same thing. Because again, our moment arm is acting up, and this is acting down. So this is weight of ladder, and this is the moment arm of the ladder. Moment arm of the person, weight of the person. And then the last one, plus, what is the magnitude of the moment arm for the last force?
2.
Times 313.6 times the sine of what?
Nine.
40.
50 degrees?
I've got 3 different answers there.
Wait, which direction, where is the moment arm acting? Is it perpendicular to the wall?
The moment arm, always from the axis of rotation to where the force is applied.
So that's 50 degrees up,
So-
and then that one's coming out horizontally like that. So 40 degrees.
I'm confused. Wait.
So that's 50.
In the last case, the moment arm from the axis of rotation to where the force is applied, it's going in that direction at that 50-degree angle there. My force is acting to the left, that angle right there.
I wasn't doing the other thing. No, 130.
This is the normal force of the wall, right?
Yes.
Okay.
So this tau sub y sub h. Tau sub w sub l. Tau sub w sub p.
So is the moment arm this way or this way?
The moment arm
For y sub h?
for which one?
For y sub h, the
It's-
last one.
That way.
Okay.
R sub h.
Because the force is being applied to the left? That's what I'm confused on.
Because it's a matter of where is the force applied. The force is applied here.
Right.
And so that's my axis right there, so.
Oh, yeah. Okay, makes sense now.
I have one equation and one unknown now. Because we already solved for the other numbers. So now it's a calculator exercise. Or algebra exercise, however you want to do it. If someone be kind enough, I obviously did not pick the convenient angle where I know the trig functions for them.
The torque of the weight of the ladder is the minus, 314.96.
Okay.
Or 0.97.
For the next number, it's 2402.32.
2402.32.
And then the number next to the X is 440.95.
440.95.
Yep.
Alright. We need to isolate x, so I'm just gonna add that to both sides, that x term, so we get whatever that is equal to 440.95x. And doing the fancy math there. Two, 4, 1, 3.25.
For the,
No.
for the
No,
difference.
no. 2113.
2087.
Say it again?
2087.35. You're getting the difference between
That's what I got.
2,400.
That minus that,
Yeah.
Yeah.
2087?
Yes.
Yeah.
And then it's 0.35.
X is,
No, 0.35
oh,
instead of
0.35. That's what I get for doing subtraction in my head. All right. And we ultimately end up with x equal to
4.73.
4.73
Yeah, that's what I got.
units? All right. He's not even to the halfway point on that ladder before that thing starts to slip. It is not safe. All right, so let's take a look at if we had gotten different answers. Obviously, I was making up numbers on the spot as we were doing that over there. Sometimes we work through all of it, we end up with x is equal to something bigger than 10. So suppose if we had gotten 12 meters, what would that mean physically?
We did something wrong. Or
Not
he could-
necessarily.
He could keep going and it wouldn't slip.
Right. So in order for it to slip, he needs to be out here, but he'd never get out there.
Because the ladder is kind of long.
If we had gotten x is equal to -2 meters, what would that have told us
The ladder already slipped.
before he even steps on it?
Well, according to my calculations, it's a very safe ladder to walk on, so something went wrong.
Now, if we increased theta, then what would change? So if we made it an 80-degree angle, then this would become
90 plus 80, right?
yeah, so that'd be 170.
170 there. And then, 20 there, right? No, sorry,
It would be,
Just 100.
10. Wait,
I made it, what, 80, I said 80 degrees, right? So if theta is 80 degrees,
it's 100.
Yeah, it's 100.
100 degrees, okay.
I don't know where I got 10.
So notice that this positive value, the sine of 100 degrees is getting closer to 1, sine of 170 is getting closer to 0. So these terms right here, the negative terms are becoming less and less. So we end up with a much larger positive number and a much smaller coefficient of x.
Which means X, which means you can walk up the ladder more.
So generally, when you set up a ladder, a 50-degree angle not recommended. 80 degrees is probably a little bit more realistic. Although I've never actually measured the, I don't know why I haven't done this yet, but when I set up a ladder, I don't usually measure the angle.
Also, it just doesn't look fun to like be at a 50-degree angle. Like I'd rather just be at a bigger angle.
Yeah, I don't want to stand on the ladder for again. I want to like to hold it.
That looks like those, or carnival.
Jacob's ladder.
Yeah,
That's what I was
things,
thinking.
yeah.
Let it spin.
I am assuming traditional ladder, and you got 2 points of contact of the building and the ground, unlike the fair things.
Yeah.
On the fair thing, why can't you just jump?
I don't know.
Because the instructions are, if you can ring the bell at the end, and I'm thinking, I could jump that much more easily than I could walk up that ladder.
Jump the whole ladder?
Yeah, why
You're gonna
not?
like, you're gonna like just spin though.
But all I have to do is just ring the bell, right? So if my hand, if I reach my hand out and I hit the bell before I hit the ladder,
Okay,
Yeah,
but
just
the
like a
ladders
walk
are
to the back
usually
and jump.
pretty long.
Okay, the ones I've seen are shorter. than-
Okay.
So, I guess this might be related to physics, but the reason why so many people fail that is because they think you need to spread out your weight. And what happens is when you lift your foot up on one side, the other side goes down. So you're constantly fighting this battle of balancing to where you don't fall over. So I don't know whether the guy said who was breaking it down said to go in the middle to keep your balance like from falling over, or if he said to just try and spread everything out and I don't know. I can't
And
remember.
make sure you always have a point of contact on each side as you go.
Yeah, yeah,
The times I've seen somebody do it, they had incredible balance and they sort of went up the middle.
yeah.
Yeah.
I don't know.
Some stuff to do for the weekend. See if, when the ladder slips and to see if you can master walking up the middle of basically a slack rope. All right, questions? And then I'll talk directly about the ladder.
Did you change the angles for both of them?
Here? Yes, once we come up with our answer, I was then taking a look at, from a physics point of view, if you make the angle steeper, which is what people typically do when they're going up a ladder, why that would actually change it.
And how did you get the 150 degrees
The 100 and,
on the bottom? The first.
no, that's a mark for the angle, that's 50 degrees there,
Huh.
and then that 90 degrees. That's where we got the 140.
How do you get the 130?
The 130, because the horizontal normal force here was acting horizontally, acting to the left. The moment arm is acting in this direction. So I want the angle between them when they're tail to tail. So my horizontal, the moment arm to where the force is applied is at that 50-degree angle because it's along the ladder. And then y sub h is acting to the left, and so I wanted this angle right here. 180 degrees is the straight angle, and so 180 minus 50.